6.2, use proportions to solve problems. In Unit 6, similarity. Equivalent ratios, which are in effect equivalent fractions, are two ratios that express the same relationship between numbers. Let's watch a short video.
Hi, welcome to Math Antics. In this lesson, we're going to learn what proportions are and how we can use them to find an unknown value. The good news is, if you know about equivalent fractions, then you already know a lot about proportions. To see what I mean, let's start with the simple fraction 1 over 2, or 1/2. Now let's look at a pair of equivalent fractions, 1 over 2 and 5 over 10. These fractions are equivalent because even though they have different top and bottom numbers, they have the same value. 1 is half of 2, and 5 is half of 10, so they represent the same amount. Okay, but to understand what a proportion is, we need to start with a ratio instead. A ratio is basically just a fraction that's used in a certain way. If you don't remember what a ratio is, you can watch our video about them. So let's imagine that a student who's a really good reader can read one book in 2 days. We could say that the ratio of books to days is 1 over 2. One book per 2 days. All right, but what if our student reads books at that same rate for 10 days? How many books would they read? Well, if they finish one book every 2 days, then in 10 days, they'll have read 5 books. So that ratio would be 5 books per 10 days. Do you see what we have here? These are equivalent ratios. Just like the equivalent fractions, they represent the same amount, so we can put an equal sign between them. When we do that, we have a proportion. A proportion is just two ratios that are equivalent or equal. And one thing that's really important to remember. In order for two ratios to be equivalent, they not only have to have the same value, they also have to have the same units. That is, they have to be representing the same thing on top and on bottom. Let me show you what I mean. This is a proportion because the top numbers both refer to books and the bottom numbers both refer to days. But what if we change the top unit of the second ratio to be pizzas instead of books? 5 pizzas in 10 days is not equivalent to 1 book in 2 days. So even though the numbers are still the same, this is no longer a proportion. Or what if we keep the same units and just switch them in the second ratio so that the days are on top and books are on the bottom? Are they still equivalent? Nope. This is not a proportion anymore either. 5 days per 10 books is not equivalent to 1 book per 2 days. So the units have to be exactly the same for both ratios to form a proportion. All right then, so a proportion is a pair of equivalent ratios. But why do we care? What are proportions good for? Well, it turns out that proportions are really good for figuring out something you don't know from something you do know, and that makes them very useful. For example, let's suppose that our student, who's a good reader, has a big stack of books that they want to read, 23 books to be precise, and they want to know how many days it will take them to finish. How do we figure that out? Well, let's start with what we do know. We know that they can read 1 book in 2 days, so let's take that ratio and set up an equivalent ratio for 23 books. The key in setting up that equivalent ratio is to make sure that the units are the same as the first ratio, books on the top and days on the bottom. We know that the number of books that they want to read is 23, so that goes on top. But the number of days it will take is unknown. So instead of putting a number there, we're going to put the letter in there temporarily to stand for the number that we don't know. This is how you'll usually see and use proportions in math. 3 of the proportions numbers will be known, and 1 will be unknown. Fortunately, if you know 3 of the numbers, you can find the missing number easily using a procedure called cross-multiplying. Cross-multiplying is just a shortcut way of doing some basic algebra to rearrange our proportion so we can find the unknown number. To do it, we first start by writing down a new equal sign because cross-multiplying will give us another equation. Next, imagine that a crisscross shape, like an X, is overlaid on the proportion. This cross shape tells you which numbers to multiply together on each side of the new equal sign. 1 and n will be multiplied together on this side of the equation, and 2 and 23 will be multiplied together on the other side of the equation. Oh, and as long as you follow the crisscross guides, it doesn't matter which pair goes on which side. Okay, so our proportion has been rearranged. Now what? Well, on one side of the new equation, we have two numbers being multiplied together. The next step is to go ahead and simplify by doing that multiplication. 2 times 23 equals 46. But what about the other side of the equation? That has a number being multiplied by our unknown letter n. How can we multiply when one of the numbers is unknown? Actually, we can't. Fortunately, we don't need to, because we're just trying to figure out what our unknown number is. What does it equal? In other words, we need to keep rearranging our equation until the unknown value is all by itself on one side of the equal sign, and all the known values have been combined on the other side of the equal sign. Then we'll have found the unknown. In this problem, getting the n by itself is easy because it's just being multiplied by the number 1. And what happens to a number when we multiply it by 1? Yep, absolutely nothing. 1 times n is exactly the same thing as just plain n. So we can just ignore or get rid of the 1. And look, our equation is now n equals 46. That means that we know what n equals. We've figured out what the missing number of our proportion is. If our student can read one book in 2 days, then they can read 23 books in 46 days. We've used a proportion to solve for an unknown. All right, let's see another example.
Okay, a couple of things to remember when you're thinking about proportions is they can be rearranged. So if you'll remember in class, we talked about the fact that you could test to see if these were equal using that cross multiplication property. So this says that if two ratios are equal, then their reciprocals are also equal. So the reciprocal means you can flip the fraction, remember? So the reciprocal of A over B is B over A, and the reciprocal of D over C is C over D is D over C. And notice when you cross multiply, you get AD is equal to BC. And on this one, when you cross multiply, you get AD is equal to BC. You just want to make sure you end up with the same equivalent statement. Also, if you interchange the means of the proportion, then you form another true proportion. So if I switch the place of B and C, and it now is C and B, I'm still going to get the same proportion. So multiplying means and extremes, that's AD is equal to BC, and AD is equal to BC. In the diagram, side MN over RS is equal to side NP over ST. We're going to write 3 true proportions. The first one is easy. We're just going to replace the names of the sides with how long they are. So MN is 8, RS is 10. So the first part of that fraction would be 8 over 10. NP is 4, ST is X. And so my proportion looks like 8 over 10 is equal to 4 over X. By this reciprocal property, I can rewrite this by flipping both fractions. So 8 over 10 is going to become 10 over 8, and 4 over X is going to become X over 4. Note that when you use the reciprocal property, you have to change both fractions. And we can test to make sure this is right. So this would be 8x is equal to 40, and this would be 8x is equal to 40. In property 3, you can interchange the means. So I'm just going to swap the place of 10 and 4, and it's going to become 8 over 4 is equal to 10 over x. And again, 8x is equal to 40 when I multiply those means and those extremes. Let's look at this figure. It says, given the proportion SQ over SR is equal to TV over TU, find our Q. So how do we begin? Well, we're going to begin by determining the side lengths for SQ, SR, TV, and TU. All right, so let's find the lengths. SQ, we don't know that one. Let's just call it X. SR, we know that one. It's 7. TV, we know that one. If we combine 3 and 7, we get that TV is 10. TU is 3. Now that we've determined the lengths of those 4 sides, now we're going to set up a proportion using these values and solve it. Our proportion looks like X over 7 is equal to 10 over 3. Notice that the X and the 10 and the 7 and the 3, the X and the 10 are for the big figure, and the S and the 3 are for the small figure. Cross multiply, and you get 3x is equal to 70. Divide by 3, and you get 23.333333, or a bunch of repeating 3's. But let's remember, what is x? X is the side length SQ. So this tells us that the entire side length over here, SQ, is 23.3. Okay, so now let's use that value to find the answer. We're looking for only RQ. Only RQ. Well, we know that RQ, the entire, this side length, is the entire side length minus this portion. So RQ is SQ minus SR. Then just plug in what you know. SQ is 23.3. SR is 7, giving us RQ as 16.3. A scale drawing is a drawing that is the same shape as the object it represents. The scale is a ratio that describes how the dimensions in the drawing are related to the actual dimensions of the object. Let's finish up this video.
Have you ever noticed that maps are a lot smaller than the real-life places that they show? A map is a good example of something called a scale drawing, which is just a drawing that's either larger or smaller than the real thing it depicts, but it's still in proportion to that thing. For example, this map of Hawaii is a lot smaller than the actual Hawaii. But even though the map is smaller, it's still proportional to the real island. And there's even a scale on it to show the relationship between the two sizes. It says that 5 centimeters on the map is equal to 9 miles on the real island. Okay, suppose that we want to know how many miles it is from the Hawaiian volcano, Mauna Loa, to the city called Hilo. We can set up a proportion to figure that out. The ratio that we already know is 9 miles per 5 centimeters. Now we just need to set that equal to an equivalent ratio that has the unknown distance in it. Because we have the map, we can use a ruler to measure how many centimeters it is from Mauna Loa to Hilo. It looks like about 20 centimeters, so the bottom number of the equivalent ratio is 20 centimeters, and the top number is the number of miles, which is unknown. Again, we'll just use the letter N to stand for that missing number. To solve this proportion for the unknown number, we use our cross-multiplying procedure. First, we write a new equal sign, and then we imagine the crisscross to show us what we multiply together on each side. On the first side, we have 9 times 20, and on the other side, we have 5 times n. On the side that has 2 numbers, we can go ahead and simplify. 9 times 20 equals 180. On the other side, we have 5 multiplied by our unknown value, n. We can't multiply that, but we don't need to. Instead, we want to get the n all by itself. How do we do that? Well, we can't just ignore the 5 like we ignored the 1 in the last problem. Instead, to get the n by itself, all we have to do is divide both sides of the equation by the number that n's being multiplied by. In this case, that's 5. So on the first side, 180 divided by 5 equals 36. And on the other side, 5 times n divided by 5 is just n, since the 5's cancel out. There. Now we know what the unknown value in our proportion is. 36 equals n, which is the same as n equals 36. That's the number of miles it is from the volcano Mauna Loa to Hilo.
Okay, let's take a look at this example. The blueprint shows a scale drawing of a cell phone. An old cell phone, obviously. The length of the antenna on the blueprint is 5 centimeters. The actual length of the antenna is 2 centimeters. What is the scale of the blueprint? Okay, so to determine a scale, we're going to write the ratio of a length in the drawing to an actual length. So we want drawing and actual, drawing and real life. Then we want to make sure that we rewrite the ratio so that the denominator is 1. The length on the blueprint was 5 centimeters. The length on the antenna was 2 centimeters. Centimeters go away. I take the 5 and the 2 and I divide them by 2 to make the denominator, or the bottom of the fraction, 1. So the scale of the blueprint is 2.5 centimeters to 1 centimeter. The scale of the map at the right is 1 inch to 26 miles, meaning that for every 1 inch on the map, it's equivalent to traveling 26 miles in real life. The actual distance find the actual distance from Pocahontas to Algona. We'll begin by using a ruler. The ruler distance from Pocahontas to Algona on the map is about 1.25 inches. Let x be the actual distance in miles. Remember, we have a scale. 1 inch is 26 miles. So we want to know how far is 1.25 inches. Let's set up a proportion and solve it. In the numerator, or the tops of the fractions, we'll put the distance on the map. 1.25 is the measured distance, and 1 is the distance from the scale. In the bottom of the fraction, we'll put the actual distances. X is the one we're looking for. 26 is from the scale. Cross multiply, and we get x is equal to 32.5. And let's put that in context. What does that mean? It means that if the distance from Pocahontas to Algona on the map is 1.25 inches, that the actual distance from Pocahontas to Algona is 32.5 miles. You buy a 3D scale model of the Reunion Tower in Dallas, Texas. That's the tower on the right that you see that's gold with the big ball on the top of it. The actual building is 560 feet tall. Your model is 10 inches tall. The diameter of the dome on your scale model is about 2.1 inches. Part A. What is the diameter of the actual dome? Well, let's set up a ratio, a proportion. 10 inches over 56 feet. That's the scale that they gave us. 10 inches in the model, 560 feet in real life. We're going to set that equal to what we want to solve for. The diameter of the dome is 2.1 inches. And we're looking for the actual diameter of the dome. Cross multiply, solve for x, and you're going to get 117.6. What does that mean? That means the diameter of the actual dome is about 118 feet. Remember, diameter is the distance from edge to edge of a circle through the center. Part B, about how many times as tall as your model is the actual building? In order to find this scale, we will need to simplify a ratio with unlike units. In order to convert to the same units, we'll have to use a conversion factor. This is an easy one because we know that there are 12 inches in 1 foot. So set it up. 560 feet over 10 multiply by 12 over 1. Inches cancel out, feet cancel out, and we multiply and get 672. We put 560 on top this time because we want to know how much taller the actual building is than our model. If they had asked us how much smaller our model is than the actual building, then we would have put 10 on top. 672 means the actual building is 672 times as tall as the model. Time to practice. You have a quizzes and then an assignment following. Good luck, and I hope you found this video helpful.